All right, so here we are identifying the hybridization in a small molecule, the hybridization of the central atom. And so what hybridization really is it's like a little bit of an additional explanation. What we've been doing so far using the VSEPR model, valence shell electron pair repulsion model to determine molecular geometry, is not really a complete enough picture to explain a lot of the things that we see in molecular geometry when studying molecules using this very expensive equipment and very sensitive experimental techniques. It doesn't answer everything. And so there are some adjustments we have to make to help explain some of the phenomena that we see. And one of these adjustments is this introducing this concept of hybridization. I won't delve too much into this idea of hybridization. I will be more than happy to answer any questions you have about it, or even maybe I may make an additional video just on hybridization or jump in during my office hours. But I found this very simple, easy to use table that really simplifies it for us to be able help us to be able to identify hybridization without having to go into all the nitty-gritty details behind it. And here's the table right here. So all this table requires us to do is to determine the hybridization of the central atom. We just need to find out the ALEKS notation. And the ALEKS notation will always correspond to the correct hybridization. It's just that easy. And we can do that because we've done it already. So let's just go ahead and draw the Lewis structure for tetrafluoroiodide. 1, 2, 3, 4. And we should have 36 valence electrons to work with here. (18, 20, 22, 24, 26, 28, 30, 32. And so I need to put a lone pair here and a lone pair of electrons there. We can count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. We haven't finished yet because, of course, this is an ion, -1 charge. Let's check formal charge just to be sure. Formal charge here is 0. Formal charge here is 0. Here's 0. Here's 0. And the formal charge here is 1, 2, 3, 4, 5, 6, 7. 7 minus 8, minus 1. So formal charges are minimized, and the sum of the formal charges is equal to the charge. Perfect. Okay? So the question is, what is the hybridization of the central atom? We determined the central atom to be this iodine atom. What's the hybridization? Which is referring to the orbitals, the electron orbitals that these electrons are in. These electrons here. These, and these. So in order to do that very easily, let's just write the ALEKS notation. The ALEKS notation is going to be A, X, 1, 2, 3, 4, E, 1, 2. Okay? That's the ALEKS notation. And so if we go here to this little cheat sheet that I've put together, we find AX4E2. It tells us that the hybridization, the orbital hybridization, is sp3d2. Okay? So the orbital hybridization is sp3d2. So this idea of orbital hybridization helps us to make sense of why the geometry of tetrafluoroiodide is what it is. If you look very carefully, how many electron domains do we have? 1, 2, 3, 4, 5, 6. Okay, that's represented here. S orbitals, S subshells have 1 orbital. Okay, so that's 1 orbital where an electron pair can go. P subshells have 3 orbitals. Okay, and they're all 3 are occupied. And D subshells have 5 orbitals, but only 2 are occupied. Let's give a count. 1 plus 3 plus 2 is 6, which is exactly the same number of the electron domains here. Electron domains is something that we talked about earlier in one of the earlier topics. Okay? And so what orbital hybridization is, it's saying that these electrons in these bonded pairs and in these lone pairs are located in these hybrid orbitals. These s, p, and d orbitals, if you remember from Chemistry 1, at the end of that Chemistry 1, you may have talked about orbitals and electron configuration. These orbitals are kind of combined and hybridized, so they're kind of joined together. So they're not really s, they're not really p, they're not really d orbitals, but a hybrid of the s, p, and d. And I have one s orbital, 3 p orbitals, and 2 d orbitals that are hybridized together. And together, they can hold all of these electrons in these 6 electron domains. And we have to go with this hybridization model because it explains the angles. The angles. It explains the angles of this particular type of geometry, whereas the non-hybridization model does not. And that's the short and sweet explanation. But use this cheat sheet that I gave you. Find the ALEKS notation and just go down the list. Find that ALEKS notation and come across and pick the correct orbital hybrid.